We have introduced PCA as one dimensionality reduction method for numerical data. The next method we're going to introduce is log linear analysis for categorical data. So log linear analysis is an extension of chi-square to more than 2 variables. Found a typo here. Okay. So earlier, remember chi-square, we have contingency tables like this. We have 2 variables. So the columns represent one variable and the rows represent another variable. And we study the interactions between those 2 variables. If they don't have any interaction, if they're independent, we expect the occurrence, the count, or the frequency for a different combination of the values going to be what's shown in the brackets. And we compare that to our observed value and to see what impact of those variables on the real counts. Extending chi-square to more than 2 variables, we will be looking at data like this. So we'll have categorical dimensions or variables. And lastly, we're going to have the count, okay? And then the goal is to study how every categorical dimensions impact the count, and if there are interactions between and amongst the variables, and what's the effect of those interactions on the frequency of the occurrences. So in this example, in our data set, people who use cigarette, marijuana, alcohol, and younger age has a count of 911 observations. Okay. So with data like this, using log linear analysis for dimensionality reduction, our goal is to identify certain dimensions that does not contribute significantly to the frequency counts. Okay, so the log linear model, if we represent it in a mathematical way, the goal is to find the simplest model, and our model looks like this. So this is the intercept, and this is the contribution made by variable A, contribution made by variable B, C, so those individual variables, if we have 3 variables. And then we have 3 pairs of interactions. And then lastly, we have one variable one factor that accounts for the contribution of the interaction amongst all the 3 variables. Okay. So it can be 3 variables, it can be 2 variables and more. In this example, we used 3 variables. The idea is to estimate those lambdas and to give us a correct, accurate prediction of the frequency f. This can be used for dimensionality reduction. For example, if we found that the contribution from A is very minimal, if A does not interact with any of the other variables, then we can eliminate A. Similarly, when we reduce the reduction, then we can reconstruct the frequency count and achieve the purpose of data smoothing. Okay. One example that I included in your R exercise looks like this. So we have the data, input data looks like this, and then we use the general linear model to create the linear regression, log linear model. And we produced a model, and this model shows us those are the lambdas, and those are the significance of those lambdas. So we can see this is the intercept, that's the very first, this very first lambda, right? And then we look at cigarettes, marijuana, alcohol, and age, their contribution to the model separately. And we can see that the age does not contribute anything significant, so therefore it's insignificant. If we look further down for the different kind of interactions, we'll see that any interaction involving age actually is not significant. Therefore, we can remove age and use after the age is removed, we compute the fitted predicted frequency, and putting them together, we can see that removing age doesn't change our prediction much. So we can use this as a way to reduce the dimension we removed age and smooth out the frequency counts for the data set. So the last group method that we want to introduce is attribute subset selection. This can be considered as another way to reduce dimensionality of the data. First of all, we have discussed redundant attributes. Through using correlation analysis, we can remove attributes that have the same value but having different attribute name. Those derived attributes that's highly correlated with some other variables. And also another way is to identify the irrelevant attributes. When we look at our data set, often with some domain knowledge, we can see some attributes probably won't contribute much information to our mining task. For example, student ID, if we are going to predicting students' GPAs, we probably wouldn't use student ID as one of the attributes. We can remove that attribute because that attribute is irrelevant. This is another simple way that can be used to reduce. So the ID example seemed to be too simplistic, right? A lot of times, those easy attributes can be easily identified and removed, but the challenges that we're facing is what about the rest of the features, and we still don't know what attributes contributes more to our problem. Contributes more information to solving our problem. As we recognize, there are 2 to the power of d possible attribute combinations of d attributes. So therefore, it's not realistic to try every combination and see which one give you the best performance. However, there are a number of general approaches that we could consider in order to perform this important function of attribute selection. It's also known as feature selection. Before the deep neural network, vast majority of the other traditional machine learning algorithms rely heavily on feature selection. Therefore, many methods has been developed, and we can categorize them into the 3 general groups. The first one is the filter method. In this method, we identify a statistical measure and try to score attributes, each of the attributes, using this statistical measure and decide which attributes should be kept. Excuse me. So such examples include using chi-square test to see which variables have correlation. Attributes does not have any correlation may not be the very good attribute to use. Similarly, correlation test does similar things. later we're going to talk about information gain in decision trees that can be used in decision tree heuristics. Information gain is a way to select the best attributes to divide to create partitions in the data set. We're going to talk more about this later. Another a general approach that falls into the filter method category is the relief-based feature selection algorithms. The basic idea in RBAs is to evaluate features or attributes one by one. And for each attribute, we look at observations. Without these attributes, so we kept these attributes in question aside, and we use other attributes to find neighboring observations that are similar to each other, that belongs to the same class. And then we observe if the fit of this particular feature in question have different values in those neighboring observations that belongs to the same class, then we reduce the importance of this feature because they don't give us good information to differentiate or grouping those. The same similar observations in the same class should have similar features, therefore similar feature values. Therefore, this difference that we observed would discount the importance of this feature. On the other hand, if we observed a difference in observations that belongs to different classes, then we would increase the importance of this feature because this feature going to be helpful for us to differentiate members of this class versus another class. The second general group of feature selection methods is the wrapper methods. This idea is what we have discussed earlier. If we have 2 to the power d possible attribute combinations, maybe we can run our algorithm on those 2 to the power d possible attribute contributions this many times, so 2 to the power d times, to see which set of attribute combination actually give us the best result. So this is also known as grid search, where you do a systematic search amongst those attributes. And as you can tell, depending on the size of D, doing 2 to the power of D rounds of computation may or may not be realistic. Grid search have the advantage that you search for all kinds of combination of attributes and your hyperparameters. You can find the best combination of those attribute selection and hyperparameters to get you the best result. However, this best result also risk overfitting problem. We're going to talk about overfitting when we start a discussion on decision trees. In general, the problem with overfitting is the algorithm performs well on your training example, but does not produce similar performance on a new set of examples. So that you have trained the algorithm to create a model that fits specifically for the data you have on hand, and therefore it's not really robust. It cannot be used effectively in another data set. This is a general problem for all learning algorithms. However, some algorithms have bigger issues than others in terms of overfitting. So since we're talking about grid search, another similar method is not to do the systematic search, try all different combinations. Instead, we put all possible combinations there and we randomly pick certain number of different combinations and find the best performing system this way. this can address partially the issue of overfitting. You are not actually testing out every combination of the features and the hyperparameters. So grid search and random search are two popular methods in wrapper methods. Lastly, embedded methods. Embedded methods refers to a group of algorithms that performs feature selection as part of the algorithm itself. So a select, you can give the system countless of the features, but the system will select what features to use. The one prominent example is decision trees. Another example is artificial neural network, where you have the input, but the system can actually disable some of the features and learn different weights to combine a large number of different weights. So those are obviously most convenient and the best way. Decision trees can be often used as the filter methods that we mentioned above. I can first run decision tree and find a good set of attributes or features, and then use these features in my in the other algorithm that I'm going to use to actually solve my problem. So decision tree being one of the steps in my entire process serve the function of selecting good attributes. I have one example here using decision trees. This is a classic example. Probably all the machine learning algorithm books, when they talk about decision tree, they use this example. The system, you are given data on a set of data on each day. The attributes describing the day is its weather outlook, humidity, wind, temperature, season. Using this data to predict if a day is good for playing tennis. A decision tree is made, which is shown here. You can see the decision tree after it does all those information gain computation, it figured out that only outlook, humidity, and wind mattered. Any other things, season, for example, doesn't matter. So therefore, temperature and season are not important attributes in predicting whether a day is a good day for playing tennis. So we talk about attribute dimensionality reduction. So earlier we talked about how to remove attributes, how to find the best attributes. Sometimes the best attributes can be created. This again, as we emphasized a couple of times, that you do need substantial domain knowledge to actually perform attribute creation task. You need to understand the factors that affect the problem that you are trying to solve. So this is attribute creation. Three general methods are used in attribute creation. First is attribute extraction. Attribute extraction is domain specific. Depending on what problem you need to solve, you need to figure out what attribute to create, to add. For example, when you already have a set of measurement data, you might actually derive means, deviation, or range, and adding those as new attributes to your data set, and see if there's it might add additional information to solve the problem. But again, you have to know the domain knowledge. I used this example because I did when I was doing a biodiversity data set. I thought using deviation would be the best representative informative attributes to add to the data set, but my domain scientists, our collaborators said no, range would be more informative. So we have to be open our mind and take the input from domain scientists to craft best attributes. The second approach is to map data to new space. So we already look at one example, PCA. So earlier we have four attributes: petal width, length, and sepal width length. And we can generalize and we can reduce it to 3, but we really map the data into this new space. So we created a new feature. In this case, it's reduced to the feature space, but we have created a new representation of the old feature. So we actually have new feature. And this new feature may actually help us to learn a better model to solve our machine learning tasks. Other examples that we're going to learn, mapping data to a new space is you can call it a powerful and useful technique and used quite frequently. The algorithm that we're going to learn later, classification and regression algorithm, support vector machines precisely used this idea of mapping data into new space to actually dramatically improve the performance of the system. And lastly, you can create new attributes by combining features. For example, you can use number of admission divided by number of applied or number of applications to create a new attribute called admission rate. Those features adds can be helpful in many cases. In general, when we're not using the embedded method, in general, we're not using embedded method, we would not know whether our attribute selection is effective or not. We have to actually run the algorithm and see its performance and compare things. So the three things, the three general approaches are actually pretty much often used in combination. Okay, this concludes this short video on the topic of dimensionality reduction.